Okay, on to our next session. So 2025 marks the UN's International Year of Quantum Science and Technology. I'm sure you're all ready to celebrate. And rather neatly, also, the 100-year anniversary of quantum mechanics itself, which I think is quite the birthday party for something that so many of us still find completely baffling. We have heard a lot of headlines promising quantum developments. But I think that for quite a lot of us, I think quantum technology still sort of feels like it's a bit magic. So I thought what I'd do is I'd get a sense of how you feel about quantum by way of a show of hands from all of you. So first things first, could you put your hands up if you don't want to vote? Oh, great, thank you everybody. Okay, hands up if you feel very well versed in this area of quantum. Okay, a few of you. And hands up if you are still wondering exactly what quantum technology is and how it might affect your life. Okay. It would have been quite embarrassing if it had gone the other way, wouldn't it? If it would have really made it awkward for this next session. Okay, for this session, we are going to separate the progress from the quantum hype. We're going to explore some of the developments for science, society, and innovation. And hopefully, in the end, you will be able to just, casually drop the word quantum into conversations without panicking afterwards. So joining me on stage, we have two brilliant minds. We have Sergio Boixo, who is Google's Director of Quantum Computing, and Professor Will Oliver, who is the Director for the Center of Quantum Engineering. And we will meet them right after this. Sergio and Will, thank you very much indeed. Okay, well, we don't have very long, but I figure we'll just start with some basics. If you could, Will, just explain to us how quantum computing is different from traditional computing.
Yeah, well, quantum computing is based on logic elements that we call qubits or quantum bits. And the way that I think of them is in contrast to our conventional transistors that we use in our conventional computers. Those transistors are basically a faucet for current. The current's on or it's off. And we call that digital 0 or digital 1. It's two states. And that's all a transistor can be. But a qubit, it's also two states. It can be in those two classical states, but it can also be in what's called a quantum superposition of 0 and 1 simultaneously. And we just don't experience this in our everyday lives. But the consequence of that is that whereas transistors can represent an exponentially large number of states, they can only represent one at a time. But in a quantum computer, you can represent all of those states simultaneously. And that's where the power of quantum computing comes from.
And that makes some traditionally difficult problems, well, once we get to that stage, incredibly easy, right?
Yeah, that's exactly right. Because classically, you would have to try, okay, I'm going to try this state, and I'm going to try this state, and I'm going to try this state. And eventually, you find an answer. But in a quantum computer, you start with a superposition of all possible answers at the same time. And as you run an algorithm, what's happening is you're suppressing all of the wrong answers while enhancing the correct answer. So by the end of the algorithm, you look at the quantum computer and you say, oh yeah, that one of exponentially many possibilities is the right answer. And that gives us a tremendous speed up, as opposed to trying things one at a time.
There has been this long-running joke that quantum computers are 20 years away, despite the fact that they've been 30 years in development, and that they're always 20 years away. I don't know, why do you think that now is the time that we should start paying attention to this stuff?
Well, I think, a couple things. One is that, I got into the field about 20 or 30 years ago. And at the time, we thought, okay, well, this is great science, and we're going to try this in a laboratory. We'll build these qubit circuits, show that they behave quantum mechanically. I mean, you can see them with your eyes. They're macroscopically big. Usually quantum is only for atoms and small things. And over time, they became more and more performant. And about 10 or 15 years ago, we lifted our heads up and said, wow, this actually works. And now we're starting to build larger and larger systems of qubits together. They still work. And in fact, now we're even, with the Willow demonstration, showing that quantum error correction can work, which is a way to preserve and maintain quantum behavior over longer and longer periods of time. The length of time it would take to actually run such an algorithm.
Well, okay, actually, Sergio, so if you could tell us a little bit about where Google is at the moment with quantum, and I think you have a Willow chip for us.
Yeah, I do. So indeed, this is let's see, there is a camera there, I believe. Well, maybe not. This is a Willow chip. And
Okay,
there you are. Maybe you can see it there. Made of superconducting qubits. The qubits are, as Will mentioned, these quantum mechanical bits that can be in 0 and 1 at the same time, in multiple states at the same time, as Will will explain. So with this chip last year, we did 2 foundational milestones, 2 important demonstrations. One is we saw a computation that we could run on this chip that will take the fastest supercomputer in the world 10 septillion years to reproduce.
10 septillion years? I mean, they're talking about billion and trillion earlier. This is like a whole other level.
A 1 with 24 zeros and is billions of times more than the age of the universe. So it's just to prove the point that some computations that are impossible with classical computers are actually going to be possible with quantum computers. This was not yet a practical application, but it's a demonstration that that is indeed true. So now we know, okay? We did it experimentally. And the second important milestone is related to what Will was saying, which is quantum error correction. So it turns out that now we can run quantum circuits with around 1,000 gates, more or less. And we can do amazing science, and we can do scientific discoveries, and we can do this demonstration I was talking about. But we believe that for most practical applications of quantum computers, when we have done studies with partners in industry and things like that, we need around 1 billion gates. So the way we're going to get to 1 billion gates from 1,000 gates is to do quantum error correction. That was a theory that was proposed, let's say, 30 years ago, and it worked last year, for the first time with this chip. We were able to show that, for the first time, normally when you put more qubits, you have more errors, and that's why the circuit fails. But we demonstrated for the first time, now we can put more qubits, and you have less errors, not more errors.
Can I see it?
We saw that last year.
I mean, to be honest, it looks like a normal chip from the outside, but qubits, not to downplay the incredible significance of this piece of technology, but the qubits, I mean, they're incredibly sensitive, right? Tell me a little bit about what makes them so difficult.
Well, a qubit, to be a qubit needs to have this property that, has to be in a superposition, which is a purely quantum mechanical property.
Hand it back to you before I drop it.
Yes, we can leave it here. It's something you cannot see with your own eyes, and that's why quantum mechanics is hard to explain. But you need to explore these possibilities at the same time in superposition, as Will was saying. And the problem is, this superposition doesn't last very long with today's experimental processors. That's the difficulty. You need to scale up to make a big quantum computer, and you want this superposition to last arbitrarily long. So that's why you need error correction, and that's the property that we demonstrated experimentally last year with this chip. Actually, the superposition lasted exponentially longer as we increased the size of the logical qubits. So we put multiple physical qubits in the same logical qubit, and the superposition lasted exponentially longer. So what that means is now we know, we have demonstrated these 2 things, right? Some computations are impossible with supercomputers. We demonstrated that. And we need error correction to run these circuits with 1 billion gates, and we demonstrated that it works. The superposition lasts exponentially longer as we increase the size of the logical qubit.
I mean, these things, they don't like sound, they don't like any noise going on around them, they don't like any vibrations, they don't like temperature. I mean, they're sort of like very, very sensitive toddlers.
Yeah, indeed. Indeed they are. And I often think of qubits as kindergartners. And so, if you imagine kindergartners on a playground, maybe 20 of them, it's heartwarming, but it's total chaos. Janie's, fallen down and gotten hurt, and Bobby's over here screaming, and everybody's running around. A great time. Again, heartwarming. And 15 or 20 years ago, our qubits were all kindergartners. But if you want to do something at a larger scale, we know that what we need to do is form teams. And I think of it as people. So clearly, if you added more kindergartners to that playground, the chaos is only going to increase. But at some point during our education, I don't know if it's middle school or high school, but at some point we get performant enough that if we put 2 or 3 people together on a team, they can outperform any of the individuals. And of course, we know this. And as the people become more performant as individuals, we can form larger teams to the point where we have companies like Google with more than 100,000 employees doing things, obviously, that no individual could do. And of course, it doesn't come for free. Now we need an HR department. We need a security department. Most of those departments aren't doing the core product, but without them, the team wouldn't function. Error correction is the same way. we're going to aggregate qubits together. Most of them are doing the job of performing an algorithm, but some of them are there to take care of the others, right? They're flagging when errors occur. They let us know. We can then go in and correct the errors. This is the way, as Sergio said, that we're going to go from 1,000 qubits and 1,000 operations up to the billions or trillions of operations that we need to realize quantum economic advantage.
Is this the reason why people talk about functional qubits or logical qubits as opposed to physical qubits, that you have to sort of cluster the kindergarteners together in a team because you can't rely on them individually?
Yeah, that's exactly right. These teams of qubits that we form, we call them logical qubits. And often in the popular press, when you see articles that say we need 1,000 qubits to do this task, they're actually talking about the logical qubit or the team of qubits working together to reach 1,000 of those. And of course, each of those teams may have 500 or 1,000 qubits, and that's how we get up to the millions of qubits.
So just tell me again, Sergio, how many teams of kindergartners are there in here?
So we have one team.
One team.
But that's for the first time this team worked together.
Okay.
And actually, this superposition lasted exponentially longer as you make the team larger. And that's what, it was proposed 30 years ago, but it was never demonstrated because the physical qubits, the kids in the kindergarten were just running around too fast. You couldn't coordinate them, put it together. They wouldn't listen, right? They were too noisy.
It works surprisingly well as an analogy, doesn't it?
Yeah, no, it's great. And what's amazing about this demonstration is we started with a team of 17. We achieved a certain error rate. And we increased that team to 49, and things got better. And we increased it to 97, and they got better still. And that's the right side of the line to be on. First time this had ever been done in any technology to show that quantum error correction works, and that was done with Google's Willow processor.
So paint me a picture then of what this actually means for society. I mean, if you have got quantum computers that can run these types of calculations in a way that traditional computers cannot, what can you therefore do that you couldn't before?
Okay, so we know, and we demonstrated that, right, that there are some problems that are just impossible with classical computers. And now we need to apply that to practical problems. And I think the main insight actually was 50 years ago. Feynman said, well, nature is not classical. The way nature works, the basic of chemistry is quantum mechanical. So if you want to simulate nature, you need to make a quantum mechanical computer. That was the insight 50 years ago. So we have actually been exploring, potential applications, right, with more detail, in collaboration with industry, and we have published end-to-end studies, and we see we can find applications in medicine, so more efficient drug discovery. I think that was mentioned in the introductory video. We see we can apply it to material science, things like more efficient battery. That's a study we did with Bosch, or even fusion energy. So we did a study with Sandia National Laboratory where we saw that certain aspects of fusion energy we will be able to address and solve with quantum computers once we have error correction working at the scale.
I guess if you have been able to get something to work down at the quantum scale, it's almost like you've created a sort of a telescope that allows you to see down at the level of atoms, right? To simulate, fertilizer, medicines, batteries, all of that stuff down at the level of atoms.
Yeah, that's right. And I have many colleagues at MIT who would call themselves quantum chemists, and they use conventional classical computers to simulate complex molecules for technical advancement. And they just can't do it in real time. That's the problem. And of course, they don't give up. What they do is they make approximations. So they're getting approximate solutions, but not the exact answer. And sometimes what we need is the exact answer, a higher quality solution in a realistic amount of time so that engineers can then take those results and design, for example, a better battery that drives for, say, 1,000 kilometers instead of 500. And these types of problems are pervasive. Right? And that's what quantum computing will help us do.
Absolutely. I mean, if you think about the impacts that doubling the effectiveness of batteries would have across the entire world, I mean, it's really, really, really gigantic.
Yeah.
There have been quantum winters before, though. I mean, as you say, this has a long history. And there have been times where, it's sort of gone out of fashion, shall we say, or there have been stalls in terms of the progress that's been made. What are the risks of another quantum winter happening before we reach this kind of great goal that you painted?
Right. So we have seen, and even with this chip last year, that indeed there are problems that are impossible with classical supercomputers, check. We have done studies of potential applications, right? But then what we see is that when we do these studies, when we compile the quantum algorithm, we need 1 billion gates, and we're at 1,000 gates. And that's why we need quantum error correction. So we have shown that quantum error correction works, right? So we can get the kindergarten, qubits to work together. But we're still at the level of 1,000 gates. And we need to get to 1 billion gates, right? So that's 6 orders of magnitude. So I think the risk is, we prove that it's going to happen. It's not a question of if, it's a question of when. But this is still a difficult engineering challenge to get there. So there is a risk, I think it's a financial risk, mostly at this stage. I think with the risk, the physics, let's say, we have clarity on some of the applications. There will be many more. It's hard to find applications without a quantum computer that we don't have yet. But it will take, reducing these 6 orders of magnitude will still take some financial investment and time.
But this thing here, really represents a kind of step change in terms of what's just on the horizon.
I will say so, right? 40 years ago, there was no theory of quantum computing, only many problems that we could not solve, right? We already knew from 100 years ago how to write the equation for any molecule, but we were not able to solve it. Feynman said, you need a quantum computers. Then people came up with the idea of quantum error correction, and slowly physicists started to believe it was possible. But unless you see it in an experiment, you always have questions, Is a quantum computer even possible? Because it sounds very strange, right? It's completely the opposite of the history of computation. For the first time, we have this completely different computational device that makes some impossible things possible. So until you see it in an experiment, you don't really know for sure that it can work. And we have shown that it can work.
We're in a room of business leaders here. Some of the horizons that we're talking about here are sort of like medium and long term. Are there things that people should be thinking about now or doing now in order to prepare for a quantum future?
Absolutely. People tend to overestimate what's going to happen in 2 or 3 years, which is why there's hype, and that's of course the danger that Sergio was talking about. But almost certainly we underestimate what's going to happen in 10 years. Quantum is a disruptive technology. We have quantum computers now. They're just small, but they're increasing in power and performance. And so what I usually tell companies at our Center for Quantum Engineering, the companies that work with us, is look, don't bet the farm. It's early days. But you need to start to form small teams within your organization, teams of people who understand your problems, and have those teams take those problems, develop quantum algorithms that can address them. And by doing that, even if you can't run those at scale on a quantum computer today, you can test them at a smaller scale on today's quantum computers. And this will also give you insight into what we're waiting for. How large of a quantum computer needs to arrive before I can take advantage of it in an economic sense. And you need to do this because the worst thing would be, of course, if your competitor does it and you don't, and then one day they're using quantum computers, and at that point it's too late to catch up.
Very interesting, actually. There's echoes of the previous section there about curiosity and learning and remaining humble. Sergio, Will, thank you very much indeed. That was fascinating. Thank you. Thank you.